Spacetime diagrams. It's very difficult to visualize situations in 3 dimensions, so situations in 4 dimensions are even more difficult. In fact, it's impossible to visualize situations in 4 dimensions. However, in 1908, Minkowski introduced a way to visualize the concept of spacetime. Minkowski showed how we can represent the 4-dimensional nature of spacetime using a graphical picture known as a spacetime diagram or Minkowski diagram. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. A spacetime diagram is a representation of spacetime obeying the laws of special relativity. It is a graph showing the position of objects in a given reference frame. Probably you have already seen lots of motion graphs. Those graphs are drawn the usual way with the on the horizontal axis and placement on the vertical axis. In relativity, it's customary to show these graphs with the axis reversed. That is, time plotted on the vertical axis and position on the horizontal axis. Spacetime diagrams are normally drawn with only one of the space coordinates on the horizontal axis and the temporal, that is, time dimension, on the vertical axis. The vertical axis shows the speed of light times t instead of t. This makes both axes have the dimension of distance. The axis represents the reference frame of a specific inertial observer. Events. Events are represented as dots in a space-time diagram. The coordinates of the event are read off from the axis. The figure below shows a space-time diagram and an event marked by the dot. Let's calculate the time in this reference frame. This event has x equals 5 meters and ct equals 6 meters. Since the speed of light is a constant everyone agrees on, knowing the value of ct allows us to find the value of t. Worldlines. An object traveling through spacetime can be imagined as a sequence of events. This sequence of events traces a straight line on the spacetime diagram. This line is called the worldline of the object. The worldline shows the path of an object in spacetime. Let's see how the worldlines work. Pay attention in this simple example. To draw the worldline of these events, we must find the times for these two events before putting them on the spacetime diagram. For event A, the times is given as we obtain the time for event B at the same way. Events are represented as dots in a space-time diagram. Event A has coordinates 2.5 and 12.5. Event B has coordinates 5 and 25. Line AB shows the trajectory of the electron through spacetime. Now let's find the speed of this electron from the spacetime diagram. Speed is equal to distance divided by time. We multiply up and down by the speed of light. So it's pretty easy to find the speed from the space-time diagram. But let's take a closer look at the speed. We can see that x divided by c times t is the tangent of the angle of the worldline with the t-axis. So it's also pretty easy to find the angle of the worldline with the ct-axis. The tangent of the angle between the worldline of a particle and the ct-axis gives the speed expressed in units of the speed of light. We know that a photon moves at speed c. Therefore, the worldline for a photon starting at the origin of the spacetime diagram is aligned at 45 degrees to both ct and x-axis. All initial observers agree on the value of c, so all observers must agree on the worldline for photon as shown on space-time diagram. Now we will see how to represent more than one initial frame on the same space-time diagram. Consider frame S', which has a reservoir speed v relative to frame S. Let us assume that when clocks in both frames show 0, the origins of the frames coincide. The origin of frame S' moves to the right with speed v. Suppose there is an object at rest at the origin in its own reference frame S'. We can draw the worldline of this object as seen in reference frame S. The worldline of this object will make an angle theta with the ct-axis. But this worldline is just the collection of all events with x' equals 0, and is, therefore, the time x of the frame S'. The ct'(x) makes an angle theta with the ct-axis. The x'(x) makes the same angle theta with the x-axis as the ct'(x) makes with the ct-axis. To find the coordinates of an event in the frame S', draw lines parallel to the slanted axis and see where they intersect the axis. In reference frame S, the coordinates of event 1 are x1, ct1. In reference frame S', the coordinates of event 1 are x'1, ct'1. An event will have different coordinates in the two frames, as we know. The coordinates in the two frames are connected by Lorentz transformations. The figure below shows the space-time diagram for two frames of reference traveling at constant speed v relative to each other. Use it to estimate the answers to the following questions. Estimate the speed of frame S' relative to frame S. The tangent of the angle theta is 3 divided by 5. But we know this is speed v divided by c. So the speed of reference frame S' is 0.6 times c. Find the coordinates of event A in relation to frame S. The coordinates of the event are read off from the axis. Event A has coordinates 4 and 4. Find the coordinates of event A in relation to frame S'. We know that the coordinates in the two frames are connected by Lorentz transformations. First, we find the proper time, and then we find the Lorentz factor. We calculate the value of the Lorentz factor to calculate the time and position measured in the second frame of reference. We use the Lorentz transformation for x prime and t prime. To find the coordinates of event A in the frame S prime, we draw lines parallel to the slanted axis and see where they intersect the axis. Pay attention.